Good. Okay, so this will be a lecture on free probability theory, and I want to give you some motivation or maybe some idea what this is about by telling you a little bit about the history of the subject, and so that you maybe get some idea what we are going to cover in this class. But then I will very soon start right away with this basic. Okay, so this is about free probability theory. And this is a quite new theory in mathematics, so probably you don't know what this is. And so this is free probability was created by Roland Speicher in the 1980s. And he created this theory by looking on, in the context of operator algebras, from Roman algebras, and there he isolated a concept which he called freeness. Okay, so that was the start of it. So, let's isolated a concept which he called freeness. This was in the context of operator algebras, but I mean, the whole thing is called free probability theory. So I mean, operator algebras have nothing to do with probability theory, but the philosophy about this freeness is that it should be investigated in analogy to the notion of independence from classical probability theory. So in a sense, it's a kind of non-commutative kind of independence. So that's the philosophy, which of course has to be made concrete. So freeness is a kind of analog of the most important notion from classical probability theory, namely independence of random variables. Okay, so this means that what we are doing in free probability theory has a kind of probabilistic flavor. In particular, freeness is also called free independence, to make this clearer. So freeness is the same, there's another name for it, is free independence. To make this analogy to the classical independence theory. And this also means that questions we are asking in the subject and we are going to answer are very similar, analog to classical questions. So the first things which Roland did in this context was to look on an analog of a central limit theorem. The central limit theorem is the most basic thing, one of the most basic things in classical probability theory, and so that's a kind of free analog. And so there's a free central limit theorem, which was done as one of the first theorems in the subject, and there's also the notion of a free convolution, which is the analog of the classical convolution. Classical convolution is the question, if I have two independent random variables, how can I describe the sum of them? This is given by the convolution of the distributions, and so there's also an analog in this context, which is called free convolution, which will be a basic operation which we have to understand. Okay, so then the subject evolved slowly, and in particular, I also made some contributions there. So namely, there's also a combinatorial theory of freeness. So there's a nice combinatorial structure behind this theory. Also there's a combinatorial theory of freeness, which was by myself around 1990, 20 years ago. And it turns out the combinatorial structure of free probability theory can be nicely described by a combinatorial object, namely by so-called non-crossing partitions. And they form a very nice, they have a very nice structure. So namely, there's a matrix of so-called non-crossing partitions. And this gives then a general theory of free cumulants, which gives a much more combinatorial approach to the whole theory. The original approach of Voiculescu was very analytic and operator theoretic, but also has a alternative approach resting on combinatorics. Okay, this is given by these free cumulants, and in particular together with Andonika, I then developed a lot of things in free probability theory, and we also have a monograph mostly on this combinatoric side. Okay, but then maybe the most important development in free probability theory was the realization of Voiculescu that actually this notion of freeness, which was introduced in this operator algebraic context, actually also occurs also in the context of random matrices, in a totally different context. So this was a big discovery by Voiculescu, maybe 10 years after the start of the subject. So he discovers freeness also in the context of random matrices and actually in asymptotic context. So if the size of the matrix goes to infinity, so asymptotically, we also have freeness for many classes of random matrices. And random matrices is also a very active and interesting new subject in mathematics. And so this was around 1991. Okay, and this somehow changed the subject quite a bit and made also free probability interesting for many different communities. Before maybe it was something more which evolved in the context of operator algebras, but after this relation with random matrices, okay, it became interesting for many other subjects. Okay, so maybe let me give maybe some kind of idea what the relations which we have. So in free probability theory, we have this abstract notion of freeness. The crucial central concept, and we'll define it soon. Okay, and then, this appeared, or actually it was modeled or defined according to something which Voiculescu observed in the context of operator algebras. Okay, so expression for normal algebras. Okay, so it's an abstract version of something which you find completely here. But then we also see that in the context of random matrices, we find asymptotically the same concept. Which in particular means that there is some kind of relation between operator algebras and random matrices. And these are very different subjects in mathematics usually without any clear connection. Okay, and so then maybe there's also, there's also a theory understanding this freeness. There are also different approaches, and one is the combinatorial theory of freeness. But then, of course, there's also a more analytical approach. More particular complex analysis methods, and all these are of course related. Of course there are exchanges between the different subjects. So some things are maybe easier to see from one side, but maybe extensions also can be done in a different way. Okay, and maybe let me say for random matrices, as I said, random matrices, the connection to random matrices opens a whole new world for free probability theory. Because random matrices are applied in many different subjects. Okay, and in those subjects, then methods of free probability theory have also become important. And for example, one very applied application is the application of random matrices in wireless networks. So, for example, one uses random matrices for modeling wireless networks, wireless communication, and then questions about the eigenvalue distribution become important, and free probability theory allows you to derive big tools and derive new results in this direction. Actually, application of freeness via random matrices to models let's say wireless communications, wireless networks, or maybe also applications to the representation theory of large groups. Well, I mean, representations are given by matrices, and okay, if you look for large groups like Sn, big N, maybe then you're dealing with large matrices, and they behave very often somehow like random matrices. Okay. So you can also describe asymptotically somehow generic behavior of representations of groups by tools, by methods, or results from free probability theory. So it also tells us something about the asymptotics, the representation theory of large groups. Also, asymptotics of large group, for example, you should think of, I mean, you have Sn, a permutation group for each n, and then you want to understand what happens for big N. For small n, you can write down everything explicitly. For large n, you might have abstract formulas, but it's not so clear what they really mean. But I mean, free probability tells you somehow about generic behavior. Yeah. Good. Okay, so I mean, there are many more relations to subjects, but the idea is that actually something which started in operator algebras, which is somehow very nice, but somehow also a small part of mathematics, suddenly you have an abstract notion there which makes a relation with this quite different subjects in mathematics. Okay, and maybe I want to say maybe a few more words about this relation between operator algebras and random matrices, because actually this was also crucial for progress on the questions on which Michael was interested in the context of operator algebras. So I mean, this relation here tells you that actually in a sense you can model operator algebras, which are quite abstract objects, by random matrices. And this modeling actually led to some really new results on the von Neumann algebras and the free group vectors on which Michael was interested. Okay. And on the other hand, I mean, this connection between operator algebras or freeness and random matrices also gave new tools for dealing with random matrices. So in particular, free probability gives new tools and also results on the asymptotic eigenvalue distribution of big classes of random matrices. And in particular, what we can do in free probability theory is to deal with functions of several independent random matrices. So usually, classically, you're dealing with one random matrix, but if you have several of them and you're taking functions, then free probability theory, and actually this notion of freeness is the basic concept which allows to deal with this. Okay, I mean, in the last couple of years, here in Saarbrücken, we have done a lot of things in this direction. So in particular, with Tobias Meyer, we have developed tools for dealing and describing functions of independent random matrices in an asymptotic regime. Good. Okay, so maybe that was kind of history, or very high-level survey I wanted to give on this subject. So are there any questions on this? Okay, no. Good. Okay, then I would go right away into the subject, and I mean, define this notion of freeness. So this is the crucial concept. So I mean, to see what really free probability is about, I mean, we should really get into it, and I should give the definition and then convince you that this is something interesting which is worth being investigated. Okay, so this is now first chapter. This is about the notion freeness, and of course I will give the definition. And of course I should also give an example, because you will see the definition looks quite strange. Maybe it's not clear where this comes from, and of course it comes from a concrete example, and this example is essentially from where Coulescu came. And then maybe we will also talk about some basic properties. Good. Okay, so here is the main definition. Okay, so first of all, I mean this notion of freeness is something which, in abstract setting, is a property of algebras, but equipped with a linear function. Okay. So, I mean, the setting we have is we have an algebra, but on this algebra we also have linear functional, and then everything is that goes back to this linear functional. And so maybe first to fix a notation, such a pair, an algebra and linear functional, we call a non-commutative probability space, which usually I will abbreviate as MCBS. Okay, so what is this? This is a pair consisting of A and phi, and the A is a unitary algebra. Unitary algebra A, so an algebra with 1, and the phi is a unitary linear function. So it's linear mapping from A to C, or functions are going to C, but it's unitary. So it should preserve the 1, so the phi of the 1 from the algebra is just a complex number 1. So unitary functional, which means phi, is linear mapping from A to the complex numbers. The unitary means that it is normalized such that phi of 1 has to be 1. Okay. So this is a very general setting. Of course, it's just notation. And of course, I mean in general, in particular in the operator algebra context, the algebras A will not just be algebras, but usually they will have more structure. They will be von Neumann algebras or C-star algebras, so they have more analytic content. But actually, I mean, the main point was that somehow this notion of freeness can be made in a very algebraic setting. So much of the things, freeness is compatible with the analytic structure which we have in addition, but it's not really a basic thing. All this analytic structure is just the add-on, and the basic stuff happens on a very algebraic level. Okay, good. Okay, so this is just frame, very general setting, and now of course we should have the notion of freeness. Okay, so what does freeness means in this setting? And freeness is a property of subalgebras. Okay, so some space. Okay, and it's not just an algebraic notion. Of course, I mean, freeness or subalgebras being free sounds like they are free in algebraic sense. And this will be the case, but actually, it's freeness, which is with respect to a given linear functional phi. Okay, so this is part 2 of the definition, and that's the most important definition of the subject. Okay, so our setting is we have such a non-commutative probability space consisting of A and phi. This is a non-probability space, and then you look on subalgebras, and they should be unitary, so they should also contain 1. Subalgebras, let's say AI, subalgebras of A, and I is running through an index set, capital I. In this can be finite or even infinite, but of course, I mean, when I'm writing down, only addresses a finite number of things. No? So it's not really a difference whether I have infinity many or just a finite number there. Okay, so I say unital subalgebras AI. They are called free. Or we are also using freely dependent. It's the same to make this analogy clearer, which we will see later. Okay, so free or freely dependent, that's the same. And the subject, of course, is freeness and free independence. In German, the subject is freeness and Freiunabhängig. I don't say we say Freiheit in German anymore. Okay, so they are free if what happens, if it's a condition of phi, and we prescribe, essentially give some relations or equations from phi, maybe that we say that phi of some terms have to be zero. So maybe I'm looking at the product phi, a1 up to ak, this has to be zero in many cases. What other cases? Whenever we have the following. Okay, so I take here a product of k terms. So let's say k is a natural number, 1, 2, and so on. And then I'm looking here on products where each factor comes from one of the subalgebras. Oh, okay. So I want that each of the HJs here is in one of those subalgebras. Let's say it's in the subalgebra IJ. Okay, the IJ is an element in my unit set. So this IJ should be an I for all the k factors which I consider here. Okay, so I have here a product of k terms, and each of those terms comes from one of the subalgebras. Then I want more. Namely, I want that each of those terms is centered, so it satisfies phi of aj is equal to 0, all j's, and then furthermore I want that I have here an alternating product in my algebra, so which means neighbors here are coming from different subalgebras. So this neighboring elements in this product are from different subalgebras. Also, this means the first guy comes from the I1 subalgebra, the second comes from I2, so this should be different. So I1 should be different from I2, and I2 should be different from I3, and so on. And I minus 1, the last but 1, should be different from the algebra of the last term. Okay, but I only want neighbors to be different. Okay, so I mean, the first and the second guy must come from different algebras, the second guy must come from a different algebra as the third guy, but the first and the third, they could come from the same algebra. There's no requirement of this. Okay, and I also don't require this in a simple way, so I mean, AK and A1 can also come from the same algebra. It's just neighbors should come from different ones. Okay. Write this down. So note I1 equal to I3 is allowed. And also I1 equal to IK is also allowed, unless k is equal to 2, and then of course they are neighbors. But otherwise this is also allowed. Good. Okay, that's the definition. Good. Okay, and of course this maybe looks like a strange, I mean, probably looks like a strange definition. So it's not clear. First of all, I mean, structure is probably not clear what this really tells us about the subalgebras. And maybe it's not, if I give this definition, it's also not clear whether there are any interesting situations where I have a situation like this. No? I mean, I require that phi of many things is 0, so it's not even clear whether this can happen anywhere. And of course, I mean, Voiculescu had an example in operator algebras where something like this happens, no? And so he made this definition. And so maybe we should look at this example. So I should give you an example where really I have this freeness of some subalgebras. And this example is more or less the example from which Voiculescu started, but not in a phenomenal algebra context, but just in algebraic context. No? Okay, so I will essentially present the algebraic version. And this is essentially talking about the group algebra of groups. And then the subalgebras are subgroups which are free in algebraic sense. No? Okay, so in the context of group algebra, this notion of freeness has a very clear meaning as an algebraic meaning. No? And then we will see that this is just a translation of this into the group algebras with respect to canonical linear functions. Here's the example. Okay, so it's an example in the context of groups. So out of group context, I should build things which I have there. And so first I should build a non-commutative probability space, which means I need an algebra and I need a linear function, which somehow has something to do with the group. And first the algebra, that's the group algebra. So the group algebra of G, which will be known by CG. So these are just linear combinations of group elements. I make out of the group. I mean, in the group I can just multiply, there's no addition there, let's say. But now I also take formal linear combinations, and so I make an algebra out of this. Okay, so what is this? So this is a group algebra. The linear structure is a complex vector space where the group elements are basis elements. So this means, I mean, elements in this vector space are finite linear combinations of group elements. So complex vector space having the basis indexed by the elements for G. So this means C of G, my group algebra, is given by sums over group elements with some coefficients which are complex numbers. So it's a complex vector space, so this alpha G are complex numbers. Those are my group elements, so I'm summing here over group elements, but of course I only want to find it. I mean, I'm not going into analytic questions. I mean, then I could go to phenomenal algebras or whatever. I could also consider maybe infinite sums, but this is purely algebraic, so it's just finite sums. So I mean, my group might be infinite, in interesting cases it will be infinite. So in this sum, I mean, there should only be a finite number of the alpha g's which are different from 0. So alpha g are complex numbers, so all g, only finitely many of them are different from 0. Okay, so that's a linear structure, and of course the addition of two such things, of course, is just adding of the coefficient. But then, of course, I can also put a multiplication on this, because I mean, essentially I know how to multiply group elements, and then just I extend this linearly. Okay, so I mean, I can equip this with a multiplication. Where if I take two such sums, alpha g times g, summing over g, final sum, and I multiply it with another sum of the same form, beta h times h, summing over h. Okay, I just multiply in a linear way, and then of course I just have to know how to multiply g with h, but of course they are in my group, so I just multiply them as I multiply the group, and g times h gives another group. Okay, so this is summing over g and h. Just again linearly multiplying it out, alpha g times beta h times g times h. Okay, then of course if I want to write as a linear combination, or in the basis of the group elements, I mean here I'm summing over g and h, and of course they're different g and h which give the same product, so I should collect those. So this, if I call this k, and I'm summing over k in my group, and then I have k, and the coefficient which I have there is the sum of all those guys for g and h which have a product k. G h such that g times h is equal to k. Alpha g beta h times k. Now this is again an element in my group algebra, and of course this sum here is a finite sum, because I mean here only finally many of them are different from 0. Okay, so there are no problems with these limits. Good. Okay, so this is now a group algebra, so this is an algebra, and of course it's also united. It has a 1, and the 1 of course comes from the neutral element in my group. Because I mean this is the guy, if I multiply with other group elements, it doesn't change anything. So if I also multiply this linear combination, it also doesn't change anything. So G is a unital algebra. And the unit, as in algebra I write it as 1. This is the same as the neutral element of E, or maybe if I write it as an element in life, as a linear combination of in this form, and I write it like this. So the alpha E is 1, and this is the element E, and E is the neutral element. Okay, so that's my algebra, my group algebra. But now I also need a linear function. And maybe I need this. Okay. So, in linear functional, okay, just as a linear object, I mean I have a vector space and the bases are group elements, so I can just arbitrarily assign values for the group elements. So, this gives me linear functional, but of course this linear functional should somehow contain important information about the group, and the important information is somehow the neutral element. Oh, okay, so essentially this linear functional will take in such a combination the coefficient of the neutral element. If I have a group, there is one element which is special, this is the neutral element, and I encode information about this in the group algebra in my linear function. So on my group algebra, we define unital linear functional. So this will be the phi, but now then we call it tau with subscript g. Okay, so we indicate it's on group algebra. So this will be linear mapping, linear functional from the group algebra to complex numbers, and I define it by just saying essentially what it does on the group elements, and then by linearity it is determined, and on the group elements it should just be a delta function on the neutral element. So it should be 1 on the neutral element, 0 anywhere else, and of course this means if I apply it to general element in my group algebra, then, okay, it just gives, it applies to G and it just gives one if this is the neutral element, so it just picks out the coefficient of the neutral element. So this is this is alpha of E is the neutral element as before. Okay, and then the pair of the group algebra and this, when they are functional, this is now a non-commutative probability space. And of course, I mean, of course, this guy is unital. So if I tau G of the 1, which is a neutral element, is 1. So I have a pair of the group algebra, and this when they are functional, this is now a non-commutative probability space. Okay. And maybe I have written the group algebra here in an algebraic way, but of course maybe you can also write it more in maybe in a way of looking at functions, and then the multiplication is the convolution. Also, maybe if you haven't seen a group algebra, maybe you have seen convolutions on groups, and then I mean this is more or less the same. Okay. I mean group algebra is more or less given by functions, or like also known. Identify an element from the group algebra, also with a function, and this function has then finite support. So this function alpha, function from the group to the complex numbers, where of course just alpha of g is just this coefficient alpha of g. Okay, so you can say, I mean, instead of writing it as this formal sum, I mean, we can say the alpha of g's are just a function which maps to each element from g, the complex number. Okay, and then if you look what the multiplication in this language means, then this is nothing else than the evolution of those functions with respect to the counting measure on the group. Multiplication evolution okay, so I mean this is a very canonical construction of algebra. But we consider it here as an analytic object. Okay. Good. So we have now a non-commutative probability space. But now, of course, we should look for subalgebras. Okay. Freeness is something about subalgebras. So we need subalgebras of our group algebras. And of course, I mean, canonical subalgebras we are getting from having subgroups of leading group. Okay. So consider now GIs indexed by I. Assume those are subgroups. Okay, and then of course, if I take now the group algebra of those subgroups, of course they are canonically embedded in the group algebra of the big group, and they are subalgebras. Okay. And C of GI. And those are now elements from the big algebra, but here in this sum I'm only running over the GI, or you can say I just have the situation that the alpha of G has to be 0 if G is not in this subgroup GI. Okay, then, so this C of GI, they are actually unital subalgebras of C of G. Of course, they are unital because each subgroup contains the neutral element. The neutral element is the same for all of them. And they are subalgebras because, I mean, if I multiply two guys where only the coefficients in this subgroup are different from 0, I mean, then, because it's a subgroup, it again multiplies only into this guy. Okay, so those are subalgebras. So talking about freeness for those subalgebras should now be something about the group structure. Okay, of course, as I said before, the name suggests the freeness which we have defined for our general setting, non-commutative probability space, should correspond to the freeness of those subgroups in the big group G. And the notion of freeness of groups, this is a very, very important thing, so maybe let me record this. So if I have subgroups, then we say they are free, and this is the free in a purely algebraic sense. So free algebraic sense. I mean, the notion of free shows up in many contexts, and usually in algebraic context it means you don't have algebraic relations between things which are free. There are no non-trivial relations. Okay, so they are free in algebraic sense, and subgroups of G, if, let me first say it in words, so if there are no non-trivial relations between different GIs in different groups. Okay. And non-trivial, of course, there are always trivial relations which are coming from the fact that, I mean, you have the neutral element which belongs to all of them. So you can multiply neutral elements, and you can say multiply the neutral element from G1 and the neutral element from G2, and I get a neutral element from G3. So this looks like a relation between the three groups, but of course this is a trivial one. Okay. Apart from these things which go with the neutral element, you don't have that A times B is equal to C, where A, B, and C are coming from, let's say, maybe different groups. Okay, but of course, I mean, to formulate this more precisely, I mean, one way is to formulate this in terms of a universal property. Very often, I mean, free objects have a kind of universal property. So absolutely, it can be formulated in terms it can also be done more concretely by really saying, I mean, what kind of relations we have to exclude, or what kind of thing. Or concretely as follows. Okay, so namely, so we want to exclude non-trivial relations, and essentially the relations, trivial ones are relations that something is equal to the neutral element. Of course, I mean, G times G to the minus 1 is equal to the neutral element. Those are trivial relations, but we want to exclude things like this, and so we can say, whenever I consider k factors, k is a number, Gj coming from one of my subgroup, then we have the following. So if each of this Gj is not a neutral element, and I'm looking at a product of them, so again neighbors should come from different subgroups. Neighbors are different, then if I multiply G1 is G2 is Gk, then this can also be not a neutral element. So this says if I multiply guys, and I mean they are coming alternatingly from different of my subgroups, and each of them is not a neutral element, then it cannot be that the whole product is a neutral element. Okay, so this is a precise version of saying what it means that the subgroups don't have non-trivial relations. Okay, this here. So I have no way of. I mean, there cannot be an interaction between G1 and G3 if there's something non-trivial in between. No? Of course, if there is a neutral element in between, then of course G1 can see G3. Good. Okay, so that's the notion of freeness of subgroups. And now the point is that actually, if I rewrite this here in terms of my non-commutative probability space given by the group algebra and this linear functional, then this is exactly the freeness definition which we have there, which somehow looks plausible. And of course, you see we have here the same kind of definition, and the only thing which essentially we have done is to prescribe the property that something is not equal to the neutral element in terms of tau. Good. Okay, so what we have is proposition 1.3, which says exactly this. So namely, we consider subgroups indexed by I, subgroups over group G, and then I'm claiming then following are equivalent. So namely, first is this algebraic condition on the level of the group, namely that the subgroups are free in the group G. The subgroups I are over I and index and I are free in G. And the second is that the same happens for the group algebras on the level of my non-commutative probability space. So, in the subalgebras, C of Gi, I running Y, they are free or freely independent. Contrast is free, I mean this is the algebraic free, and this is really our notion of freeness, which we call freely independent. So they are freely independent in the non-commutative probability space consisting of the group algebra C of G and this linear functional tau G. Let us prove this. The proof, of course, is quite straightforward, but this is really, this shows us that at least our definition makes some sense. It rewrites this algebraic notion of freeness for the subgroups into more algebraic condition. And of course, on this level, I mean, it's not, but if we just be interested in the group algebra, it doesn't make much sense to rewrite it in this form, because, I mean, algebraic level, we can also say that we don't have algebraic relations between things. But if one goes over to infinite sums, like one has in von Neumann or C-star algebra, then, of course, I mean, this algebraic notion of freeness doesn't make sense anymore. To say that infinite sums don't have algebraic relations, that's algebraic, you cannot really deal with this. Okay, but if we have a formulation in terms of a linear functional, then in this context, this linear function also has some continuity properties, which ensures that the definition of this free independence also goes over to some closure. Okay, and then, I mean, it really makes sense to formulate it in this way. Good, okay, yeah. So let us see here. So we claim we have those two things are equivalent, so we have to move two directions. Let me start maybe with going from 2 to 1. That's totally straightforward. Where we just have to observe that what tau really means. Okay. Proof. Let's say 2 to 1. So we assume that the subalgebras are freely independent, and we want to show that the subgroups are free in G. Okay, so what do we have to show? Subgroups are free in G. So this was this condition here. So we have to take this situation. We take elements from our subgroups, alternating elements. Each of them is not a unit element, and we want to show that the product also is not a unit element. So we consider this setting. So we have K, the number of factors. Then for each J, we have Gj, which is for one of the subgroups, the Ij subgroup. And of course, an element in the group is of course also an element in the group algebra. So this element is a special element in group algebra. Then we assume that neighboring elements are coming from different subgroups and hence also from different subalgebras. And we assume that each of those elements is not a unit element. Okay, and now we have to rewrite this in terms of tau, because now we have to use the freeness in the non-probability space sense, which means we must use the tau, and of course this here means nothing else but that tau g of the element gj is equal to 0. No? Because what does tau g do? If I have a formal sum in my group algebra, it takes out the coefficient of the neutral element. Here I have now an element which is in a group algebra, but it's a very special element, special form, namely it's just a linear combination of exactly one element. And this element is not a neutral element. So if I pick out the coefficient of the neutral element, this is 0. Oh. Okay. So this is exactly the same in this. Oh. So if the tau g, if I apply it to elements in the group, which of course are elements in the group algebra, then the tau just distinguishes the neutral element from all the other elements. Oh. It is 0 on all the other elements, it is 1 on the neutral element. Good. Okay, but now I'm in a setting where I can formulate things in terms of tau, and I'm multiplying elements, and the definition, I assume I have 2, which means my subalgebras are freely independent, and now I multiply alternating elements from subalgebras. All of them are centered, so tau of them, each of them is 0, and then the definition of free independence, which is what I assume here, says that tau g then of the product is also 0. Tau of g1 up to gk is also equal to 0. That's now the definition of freeness in group algebra. But again, this is just an element in group algebra, which is of the specific form. It's just a linear combination of exactly one element of this element. And tau g, the coefficient of the neutral element, is 0, which means this element is not a neutral element. This means that g is not equal to a neutral element. Okay, and that's it. So this is just observing that for group elements, tau g is exactly telling me whether it's the neutral element or not. Okay. In the other direction now, there we have to do more or less the same, but also putting it together with this linearity. So this is a little bit more advanced, but not really much. Okay, so now we assume that we know that the subgroups are free in G, and we have to see that the subalgebras are freely independent. Good. We want to show the subalgebras are freely independent, so we have to take elements coming from alternating on the subalgebras such that each of them vanishes under tau. So, consider the setting. So, to prove this free independence, we should take elements aj, which we want to multiply, and each of them should come from one of the subalgebras. Okay. So this means it has to form the sum alpha g, let's say j, g, but g is now from one of the subalgebras, and this means I'm summing here over one of the subgroups. C of G and J. Oh, okay. And I have this for, I take this for J between 1 and K. I want to multiply K elements. And those elements are of this form. Oh, J element is coming from the ij group algebra, so it can be written as a linear combination of elements here. And what are the conditions on these elements? First of all, I mean, they should come alternatingly from different subalgebras. So, as usual, 1 should be different from 2, 1 different from 8. So the neighboring groups should be different. And then, we also require that tau of G, aj, should be served. And what does this mean? Our G of aj picks out the coefficient of the mutual element. So this means in this sum here, the coefficient of the mutual element has to be served. So it can be more or less arbitrary combination of elements for my group, but the mutual element should not appear. So this here means, as before, alpha e j is equal to 0. So the coefficient of the mutual element in this sum for the j element, so j here is the index which j I have here, and g is the sub-index which tells me the coefficient of each element I have. So this should be 0. Good. So that's my input. And then for showing this freeness, I should now show that if I multiply those elements, then tau on them should also be 0. So I should now calculate tau applied to the product. So here my definition. I mean, I have to show that this is equal to 0 whenever I have a situation like this. Now I have a situation like this, and now I have to see that this is equal to 0. This calculation. So I have to calculate here. So tau g and multiply a1 up to ak, and I'm just of course plugging in. I mean, each aj is this linear combination. So I have here tau g of, so a1 is the sum of g1 from the group gi1. Alpha G1, 1, G1, so I'm calling over which I sum here G1 and so on, and here I multiply with the element AK, and there I'm summing over GK from the group G by K. I have the coefficient alpha GK, kth element, GK. Okay, so I just have plug in my form of aj, and now of course I just multiply this all out, and tau G is linear, so it commutes with the sums. And of course, the alphas are just complex numbers, they are just also coming out. And the tau is just applied to the product of the G's. So we have here is the sum. So all the sums, I'm summing over G1 up to the Gk, so I have k sums. I write them together, so it's G1 to this group G I1 up to Gk, Gik. Then I have those coefficients. So this is alpha G1, the first term, up to alpha Gk, the kth term. And then I apply tau G to the product of the corresponding G's. Good. And I better should see that this thing is equal to 0. That's what I have to prove. So I have here sum over guys, and I want to see that they are 0. Okay, to see this, I should see that each of those terms are 0. And I mean, this can be 0 either because the product of the coefficient is 0 or because this thing is equal to 0. Okay, so if this product is equal to 0, that's okay. So let us assume we have a term where this is different from 0. Then we better should see that this is equal to 0. So I assume we have here G's, G1 up to Gk. We are summing over all of them. So fix the choice of them. And if you assume this is different from 0, so this is a product of numbers. So this means, of course, that each of those numbers must be different from 0. So this means all those alphas here must be different from 0. And all alpha, which I have here, G, J, the jth element is different from 0. Yeah, what does it mean to be different from 0? This means that yeah. So what do we know? I mean, we have our assumption that about the alphas, we know something about them. Namely, some of them are equal to 0. Namely, the alphas corresponding to the neutral element. So this means if I want to have here something for which the coefficient is different from 0, then this element here cannot be the neutral element. Because the coefficient of this is equal to 0. So this means that the Gj cannot be the neutral element. Because the coefficient of this is equal to 0. Okay, so this means that all, if I have a situation here where the product of those coefficients is not equal to 0, then the G's must all be different from the neutral element. Yeah, but then I'm here in a situation where I'm multiplying elements for my subgroups, and the subgroups are coming alternatingly. Each of the elements is not a neutral element, and then the definition property of freeness of groups tells me exactly that the product can also not be a neutral element. So this means by my assumption 1, because I assume the subgroups are free, this means that the product of the G1 to Gk can also be not the neutral element. Yeah. But then, if I apply tau to a group element which is not a neutral element, I will get 0. Because tau on the group elements is exactly 0 for things which are not the neutral element. So this means tau G, G1, Gk is equal to 0. And this means here in this sum, I mean, there are situations where this guy here might be different from 0, but then it will happen that this guy is equal to 0. Okay, if this guy is equal to 0, then I don't care about the value of this. Because then the product is 0 anyway. So the whole sum is equal to 0, because each term is 0. Good. So are there questions? So this shows, I mean, this gives some motivation, I mean, for making this definition. No? But it also shows what it really on this level means. It's rewriting this algebraic condition on subgroups being free in algebraic sense into a different language. So, of course, the point of the question is, does this make any sense to this different language? So why should we rewrite it? I mean, not much has happened here, no? But it will turn out it's really a good way of rewriting. But maybe, as I said before, one reason that such things make sense is that if I go from this algebraic, this group algebras to closures of the group algebras in some topology, and I take sister of von Neumann algebras, then actually I'm dealing with infinite sums. And then it's very hard to say what does it mean if I have sub-algebras corresponding to infinite sums are algebraically free. Because for infinite sums, then you have to deal with the notion, with the question of convergence. I mean, for finite sums, it's clear what it means to be zero. But for infinite sums, of course, you might have a convergence to zero, and you might have this in different ways. So you have to encode this in a state, in a linear function, which has the right continuity property, so that you can still deal with it. Right? So this means, if one goes over here to the von Neumann algebras, for example, then this notion of freeness goes over to the corresponding von Neumann algebras. And that's a setting where we put as good. And later in the course I will come back to this. I will talk about von Neumann algebras and those things. So at the moment, we have to know what this means, but I will explain. So later we will really see what this free probability theory allows us to get about von Neumann algebras. Okay, then maybe let me just make this remark. So let me just take this free dependence also goes over to algebras. They also contain infinite sums, the limits of finite sums, which contain infinite sums. Oh, okay, this freeness also goes over to operator algebras, the algebraic notion of freeness. Way of also dealing with this in more general context. Good. Okay, so that was an example which shows at least that this definition is not empty. No? There are situations where we really have something like this. Well, of course, I mean, if you see this definition, it's not even clear that there are actually situations where you have something like this, but of course the definition was made according to what happens in the group algebra or free product of groups. Good, okay, so this at least makes sense. There's a situation where we have something like this, but of course it's not clear what this really means, this definition. And so how should we understand it? How does it help to make such a definition? And that's what we want to address next. Free independence of subalgebra really tell us what kind of information does it give us about the subalgebra. And this crucial information, the crucial observation is that actually this definition of free independence, this condition that subalgebras are freely independent, tells us or gives us a way of calculating our linear function of phi on, if we know it on the subalgebras, then we also know it on the algebra which is generated by the subalgebra. So it really tells us the value of phi on, let's say, the algebra if we know it on the subalgebra. And so that's the crucial observation, that's the next proposition. And this then also makes the contact somehow with more probabilistic ideas. Here's the statement. Position. So now we are back to the general frame. Huh? So we have a non-commutative probability space that we define the non-commutative probability space. And assume that we have subalgebras which are free independent. That is non-probability space. And unit subalgebras I is running over index set I be free or freely independent. I mean, now I always mean free in the sense of our notion of free independence. If I have a non-commutative probability space, the probability spectrum is fine. Okay, and then I'm saying that if I know phi on the AIs, then it is determined, okay, maybe not on the A, because the A might be much bigger than the AIs. But it is determined on the algebra which is generated by the AIs. I mean, its A might be a very big thing, where much of it has not much to do with the AIs. Okay, so where I get something is on the algebra, which is generated by the AIs. So E is the algebra generated by the AIs. So it's anything which I can get by multiplying and adding things from the AIs. Of course, it's a unit to subalgebra A set. Well, the claim is now that the value of phi on this B is determined by the value on the subalgebras and this freeness condition. So then phi is restricted to B is uniquely determined by the knowledge of phi restricted to each of the AIs. I should know what is phi, what elements from AI, and of course by the freeness condition, and by the free independence condition. Okay, so that's still quite simple, but a very important observation. Okay, let us prove this. So what are elements from B? I mean, every element from B can be written as a linear combination of products from elements of the various AIs. I mean, the algebra generated by the AI are just elements which I can get by multiplying and adding things from them. So, elements in B linear combinations of products where the factors are coming from some of the AIs. So of product from 1 up to k for an arbitrary number of k of factors, n, and the a's here are coming from one of the subalgebras. So aj is from Aij, where Ij is from an index set, so Aij is one of my subalgebras, and of course a priori, I mean there's no reason to assume that A1 is different from A2, but of course if they are coming from the same algebra, I just can multiply them together and then I just have another element from this algebra. Okay, so a priori, I might have here the situation that neighboring elements are coming from the same algebra, but then I just multiply them together, and then it's just, this product is just another element from this algebra. And so I multiply as long things together until I write it in a form where neighboring elements are coming from different subalgebras. And then I'm very close to what I have here. Okay, so elements in B are linear combinations of such products, and in these products, the terms are coming from the individual subalgebras, and I can also assume that neighboring elements are coming from different subalgebras. Also assume that we have exactly neighboring neighbors are coming from different subalgebras, so it's our usual condition that one is different from two and so on, different from like k. Okay, so general elements in B are linear combinations of such terms, and what I have to show is that phi is uniquely determined on such terms. Phi is linear, so of course it's enough to see that it's uniquely determined on such guys, because then by linearity it goes over to linear combinations. So we should consider such a guy and see that the value of phi on this is uniquely determined by the value of phi's on the subalgebras, from where the a's are coming. So consider such A1, A, B, and what we have to show is that the value of phi in this product, which k is uniquely determined by our knowledge of phi applied to elements in the subalgebras AI. Okay, now a priori this is not clear because the definition of freeness of course tells us something about some values of this form, but there we multiply things coming alternately from different subalgebras, but there we also assume that each of the terms is centered, phi of them is 0, and then freeness tells us that then this phi is also 0. But here, of course, in general, we don't have a situation where each of the phi's is equal to 0. So for this special situation, the definition tells us right away what the value is, and it is 0. But of course, there are many other possibilities which are not 0. And we have to see that essentially we can reduce this situation to the definition of freeness. Okay, and the proof will now be by induction on the length of such a program. Proof is by induction on k. And of course, the smallest k equal to 1 is trivial, because then I have a product of one term, so it's just 1a, and this must come from one of the subalgebras. But in the subalgebras, I already know phi. So k equal to 1 is of course clear, because then I just have a1, and this comes from the subalgebra a of I1, but of a of I1 I know what the value of phi is. Okay, so when it's getting more interesting, is I multiply more things coming from different subalgebras. Okay, so let's do the induction step. And the idea, of course, is to reduce the situation as I have it in the definition. So if I would multiply these alternating things where each of the factors is centered, phi of each of the factors would be 0, then I would know what the result is. Here I have a more general situation, but I can reduce this somehow to this centered situation by centering more or less all my variables. Good. Okay, so let's consider this case general k. So we set our variables. So this means if I have my aj, I define aj bubble, 0, that's the centered version. So I take aj, and then I subtract phi of aj times 1. And the point, of course, is that phi of this guy is now 0. And by centering things, I'm not leaving the subalgebra in which I am. Because my subalgebras are unitary subalgebras, so they contain the 1. So aj is in this subalgebra, and then I'm subtracting a multiple of the 1, so I'm staying in this subalgebra. So I have now an element which is still quite close to the aj, but it has the advantage that it is centered. Phi of a j bubble, so this is of course phi of a j minus phi of this guy. This phi of a j is a complex number, this comes out, and then I have phi of 1. Well, now you see, it's crucial that phi of 1 is equal to 1. And then of course this is equal to 7. Okay, but to put it another way, we can write the aj as this aj 0 plus the multiple of 1. Okay, and the aj zeros, those are the guys which are centered, which appear in our definition. Okay, so with this, now look at what I want, phi of a1 up to ak. Now I want to see how to determine this. Now I write this in terms of this aj 0. This is phi. And a1 is now a1 0 plus phi of a1 times 1 multiplied up to ak, and this is ak 0 plus phi of a times 1. Yeah. Okay, now hopefully it's clear what I'm doing. I multiply this out, and I will get one term which has the length k, but there I'm just multiplying the center guys. So this is phi a1 0 times a2 0 and so on up to a k 0. So here I take all those center guys, and then I get plus the rest. The rest is I'm multiplying sometimes the 0 version with this phi version. Okay, and this term here, this is now really a term which the definition of freeness tells me what this is. Because I'm here in a situation I have alternating elements coming from alternating different algebras, and phi of each of them is equal to 0. So the definition of freeness tells me that this thing here is equal to 0. And for the rest I can apply the induction hypothesis, because what I'm doing there, I'm multiplying elements. Okay, I'm multiplying some of the aj zeros. But for other terms, I take a multiple of 1. And of course, a multiple of 1, I just multiply with 1, and then I get a term where I'm multiplying less terms. And maybe, in some terms, if I have 1 there, then maybe two things are coming together from the same algebra, but then I just multiply them together, and it's getting even shorter, what I have. So I'm getting, in any case, all the terms which I have here are also of such a form, but now with less factors. And by induction hypothesis, I already know that I can express those in terms of the value of phi on the subdivisions. So this here, by induction hypothesis, first of all, this is the sum of terms of smaller lengths. The length, I mean, if I write it as an alternating products of guys coming from different subalgebras, then it has less factors, so it's a smaller length. And k, okay, but I mean, by induction hypothesis, I assume that I already know phi of those terms. So, these terms are already determined by induction hypothesis. Okay, but this tells me, if I know how to calculate those guys up to length k minus 1, I also know how to calculate it up to length k. Okay, this means I can calculate it for any length. And that's also for all linear combinations, and thus for all elements in my algebra. Good. Okay, so this shows that in principle you can calculate or reduce every such moment to such expression to corresponding values of phi on the subalgebras, but of course this is not very explicit. And then, so next time we will see via examples how to do this and maybe try to get a bit more feeling for what we have here. I mean, a lot of free probability theory, or at least at the beginning, you really should understand this formula how to express these mixed moments in terms of sub-moments in a more concrete way. We should get a better understanding for this formula. Good, but I think we stop here for today.